Integration using substitution, we talked about it very briefly before. Now we're going to look at it a little bit more formally, and in fact we'll probably revisit it again when we look at extension 2 integration as well. The basic idea though for integration of substitution, why do it? What you're trying to do is turn your integral into some standard form, something we recognise. The ones that appear on the resource sheet. So they give you this one, so that's the one where we create the derivative outside a function x to the power of n, which allows us to just add 1 to the power over the power. The trig ones are there, so derivative times sine, derivative times cos, derivative times sec squared, so those 3 are on the sheet. The exponential one, again we want to create the derivative out the front. The log, derivative over function, is on the sheet. They also give you the one where the base is not e for exponentials, so that's on the sheet as well. Interestingly though, they don't give you the one where the log's not base e. Strange. And then the inverse trig ones, the most recent ones we've seen. So the inverse sine, they don't mention that that is also minus the inverse cos though on the resource sheet, which I find strange. But of course we could use it as minus the inverse cos and inverse tan. So they're all the integrals that appear on the resource sheet. So if you're ever unsure, just double check and make sure we get it right. All right, so using substitution. In extension 1, they usually give you the substitution to use. Sometimes in extension 2 they will, but not as often as they do in extension 1. Now the thing is, if they tell you to use a particular substitution, then you must use that substitution, which is a real shame in a lot of cases, because you might just look at this one and go, oh yeah, okay, well look, derivative on function, I can create the derivative on top and just get the answer. Unfortunately, we've got to use the substitution. So all right, u is 4x squared plus 8x minus 7. So there's our u on the bottom of the fraction. The u would be 8x plus 8 dx. Well, we don't quite have that. We've got x plus 1 dx, but basically there's du, but it's 1/8 of it. So this becomes 1/8 of du on u. It's now in a standard form that we should recognise. That's our log. So we know it's an 1/8 log u, and we substitute back in, and there's our answer, an 1/8 log 4x squared plus 8x minus 7. So that's the basic idea. Let's do this one. They've told us to use u equals log x. Now, had they not told me, I mean, that would be the logical one anyway, because you're looking for things that are creating the problem, and usually it's whatever's raised to the power, you know, whatever's in a square root sign, that sort of thing is what you're looking at. So u equals log x, so du is dx on x, so we've ended up with du on u cubed, putting that into negative indices, u to the power of -3, add 1 to the power over the power. I always like to answer it in the form that it's given, so they didn't have negative indices, so I put it back to -1 on 2u squared, substitute back in, and we have our answer. Here's one from a few years ago, a definite integral. Use the substitution u equals 1 minus x. So if u is 1 minus x, du is minus dx, but remember it's a complete substitution. So we also have to substitute for those limits. The limits they've given us refer to x. Our new integral refers to u. So let's see what happens to the limits. When x is -3, u becomes 4, and when x is 0, u becomes 1. So let's substitute in completely. We end up with minus the integral from 4 to 1 of 1 minus u on root u du. But the nice thing about that is I can split that fraction up into 2 terms, and I get 1 on root u minus root u. We can integrate both of those. We end up with 2 root u minus 2/3 u root u. Now you notice I didn't bother putting that back in index form, and I guess it's because, and hopefully you'll get to this point as well, you see the square root of u and 1 on the square root of u so much, it sort of becomes a non-standard integral, if you like. It's not on the resource sheet, but it's one of those ones you just remember. I mean, you see 1 on root u, you know it integrates to be 2 root u, you know, that sort of thing. So I've just jumped straight to it. Substitute the numbers in, minus 8 on 3. U equals cos squared. This one came from 2019 HSC. Okay, if u is cos squared, du becomes minus 2 cos x sin x. But looking at what they've given me, I'm actually going to change that. Because remember, 2 sine x cos x is sine 2x. So if I go to that, I can substitute straight in there for the sine 2x. Let's work out the limits. So there we go, they become 1.5. So we end up with minus 1/2 du on 4 plus u, which is our log situation. So we get the log of 4 plus u, and you'll notice with this one I didn't bother with the absolute value signs because when I substitute in, I know I'm going to get positive numbers anyway, so I didn't worry about it. We end up with log of 10/9, 2017. Here, notice u is not the subject of the substitution, x is instead. So x is u squared minus 1. When you do use it this way, x equals function u, just need to be careful with what you're substituting in the numbers and it satisfies the domain. Sometimes, it's very rare, but sometimes you might get a problem. And if that is the problem, you might go, oh, well, that's because of the way I've written my function here. Because I've got x equals u squared minus 1, perhaps it should have been the other way around and I should have gone u equals the square root, you know, that sort of thing. But they've told me to do it this way, so there shouldn't be an issue. X equals u squared minus 1 means basically u is the square root of x plus 1. But dx will end up being 2u du, so I can sub that straight in for the dx. The limits, they'll change to 1 and 2. Let's see what we end up getting. So we've got u squared minus 1 over u times 2u du going from 1 to 2. Oh, it all rhymes, u's and 2's. 2 from 1 to 2 of u squared minus 1 du. Add 1 to the power over the power, sub in, and we get our answer. The extension 1 questions usually don't turn out too bad. And I'll tell you what, after all the integration we end up doing in extension 2, we should be nailing the extension 1 substitution questions. We should be getting those. Okay, let's have a go at these.